Okay, I'm going to work through exam 2 from this semester, starting with problem 1. So in this problem, it says a uniform electric field of magnitude 1,000 newtons per coulomb points in the direction shown. So that's along these lines here. Calculate the electric potential difference VB minus VA between the points A and B. So between this point here, A, and this point here, B. So we're going to take a charge and move it from this point to this point, and that's going to be against the electric field. So if we put a positive charge here in this field, it would tend to move with the electric field, so along these lines, and we're going to move it in the opposite direction. So we're going to need to move it from A to B while pushing in the direction of A to B. And so our force and our motion are in the same direction, so the force is going to be positive. So we can cancel all these negative answers already. And so we have D through F are possible. And so the magnitude now of that, the potential difference, is the work done to move a charge from there to there, is the force times the distance. This is the force per charge, which is the same as the electric field. So that's 1,000 newtons per coulomb. And the distance, this is a 3, 4, 5 triangle. So the distance is 5 centimeters, and you get that the potential difference is, let's see, 50 joules per coulomb, which is 50 volts. So the answer is F. Okay, for part 2, it says shown are 4 charges of equal magnitude arranged at the corners of a square centered on the origin with signs as indicated. And we're supposed to choose which best describes the electric field out of this column here and which best describes the potential out of this column here. So the electric field will point toward negative charges and away from positive charges. These two positive charges cause an electric field that will be in this direction, since the components so if you're along this line, you're sitting at the origin, the components in the y direction from either of these two charges will cancel, and you'll be left with something in the x direction. And same for these negative charges, the components in the y direction will cancel since they're both equally separated along the y direction, and so you'll just be left with something pointing along negative x. So the answer is B, that the electric field's along negative x. And now for the potential, each of these charges contributes some amount to the potential at this point. And each positive charge contributes an amount, so V positive is KQ over R, and V negative is negative KQ over R. And there are 2 positives and 2 negatives, so those will just cancel. And the potential at the origin is 0. If we were calculating the potential at some different point, it wouldn't be 0 because these distances would be different and wouldn't cancel. Okay, so part 3. Your electric space heater draws 12 amps of current through 120 volts. If electricity costs 21 cents per kilowatt hour, how much does it cost to run the space heater from November through February, so for 120 days? Okay, so we want to know how many kilowatt hours will we use from November through February, so for 120 days. And then we want to know how much power are we drawing at that time. So the power is the current times the voltage. So it says we're drawing 12 amps and at 120 volts. So that is 1.44 kilowatts. So we're using a power of 1.44 kilowatts for 120 days. So to put that in, to get that in hours, 120 days times 24 hours per day is the total number of hours that we'll use this. So that is 2880 hours. So through November through February, we're using 1.44 kilowatts times 2880 hours, which is 4,147 kilowatt hours. And each of those is 21 cents. So 4,147 kilowatt hours times 21 cents comes out to $870 about. So that's E. Okay, now how much current, this is part 4, how much current is flowing in the 200 ohm resistor on the far right? So there's the circuit here, a 44 volt battery, there's a 100 ohm resistor that's in series with this whole part of the circuit, and in here you'll have current flowing through one branch and current flowing through the other branch. And we want to know how much current is flowing through this part of the circuit here, through this resistor. So to do that, we'll need to know how much total current is flowing, and then how much is flowing through this branch. So we can find how much is flowing through this branch by finding what is the voltage from here to here. So if we find that voltage difference, we know that there's a total of 100 plus 200 ohms, so 300 ohms between here and here. Then we'll know that the current through that is the voltage. Let's label these points A and B. So the voltage between A and B divided by the resistance. That'll be voltage between A and B divided by the 300 ohms that are the effective resistance of that branch. So to find the voltage between here and here, we need to find what the total current is in the circuit. So the voltage between here and here is the same as the voltage between here and here, since this is all the same voltage. So if we know the total current through the circuit, then we can find how much is dropped across this 100 ohm circuit and subtract that from the total voltage in the circuit, or we could just find the effective resistance of this and then multiply that by, or divide that by 44 volts. So let's see. So what we have here, we have a 300 ohm. Let's redraw the circuit. So we have our battery. We have 100 ohms here. We have 200 ohms here, and an effective 300 ohms here. So these two resistances are in parallel. So if we redraw that with a new effective circuit, we'll have a battery, 100 ohms, and then this R effective from this whole side of the circuit here. And we want to know what that is. And now on this circuit diagram, the points A and B are these 2 points. So our effective for these two parallel, parallel resistances is 1 over 300 plus 1 over 200 for these two here. So this, if you do this, you get R effective is equal to 120 ohms. So now you have a total circuit resistance of this 100 ohm resistor plus this 120 ohms, since these are in parallel. So that's our total of 220 ohms. So now you know that you have 44 volts in the circuit and 220 ohms total. So the total current in the circuit is 44 volts over 220 ohms, and you get 0.2 amps. And that 0.2 amps is what's flowing through this resistor, and then part of that 0.2 amps will go through here and part will go through here. And then it recombines and 0.2 amps will go back into the battery. So we have 0.2 amps going through the circuit, and some of that is going through this resistor here. We know that 0.2 amps across this effective, we found that we had an effective resistance of 120 ohms here. So that means that, so between A and B, so 0.2 amps times 120 ohms will give us 24 volts across A to B. So this VAB here is 24 volts. So now we know that the current from A to B is that voltage that we just found. So 24 volts divided by the resistance between A and B, which was 300 ohms. So 24 volts across 300 ohms gives us 0.08 amps, and that's the answer. So A here. And so we had 0.2 amps total in the circuit, which we found by finding the total effective resistance. And then we saw that that split, that caused a voltage difference between A and B. And that means that some of the current went this way and some of the current went through this branch here. And we found that 0.08 amps went through this branch on this side.